Hello all. So in this video we will see what is a threshold voltage. So as we know, before threshold voltage your MOSFET will not start conducting, or threshold is like a trigger point to start your MOSFET. So what we say, if your VGS is less than VT, then your MOSFET is off, correct? And once you increase the voltage to greater than VT, there is a channel between drain and source and your MOSFET starts conducting, correct? So what we can say, we have to apply minimum gate voltage at the gate terminal so that it will form a channel between the drain and source, correct? So that will invert a channel and your current will start to flow. So that's what we have written, minimum gate to source voltage, or the VGS, required to accumulate sufficient number of carriers and to form a channel between source and drain under the gate, correct? So if we see here, this VGS we have written, so we have to apply a gate voltage here. So let's say this one is applying positive, it will attract negative or electrons here, and this will form a channel, correct? Once this channel is formed, there will be a flow of current, or there will be a flow of electrons, and in turns we will get the current. So this VGS we are saying as an threshold voltage. So this threshold voltage is not constant, and it depends on quite some parameters. So we will see how the threshold voltage is varied. So if we see equation of threshold voltage, Vt is equal to Vt0 plus gamma VSB plus phi minus phi. So what is a Vt0? First, Vt0 is a threshold voltage at VSB equal to 0, or source to body voltage at 0. So if we put VSB equal to 0 here, what we will get? Vt equal to Vt0 plus gamma phi plus 0 minus phi. So Vt is equal to Vt0. That's what we have seen. That's what we said. Your Vt0 is equal to the threshold voltage at VSB equal to 0. What is the other term we have seen? Other term is a surface potential. So what is a phi? Phi is a surface potential. Phi depends on, or equation of phi is Vt 2 Vt ln Na by Ni. So what is a Na here? Na is called a doping. If we are using a N channel MOSFET, it's Na. If we are using a P channel MOSFET, it will be Nd. What is a gamma? Gamma is called a body effect coefficient. So if we see equation of this gamma will be 2q epsilon naught Na by Cux. What is a Cux? Is a oxide capacitance, and what is a epsilon naught is like permittivity. Na is a doping, Q is a charge. So if we expand Cux, it will be epsilon naught x upon Tux. So if we see here, gamma is equal to 2q epsilon to Na upon epsilon to x upon Tux. Vt is directly proportional to gamma, and gamma equation is given here. So we can see, if we are increasing your thickness oxide, if this thickness oxide is increasing, your gamma will increase. If gamma will increase, your Vt will increase, correct? So what we'll see, if thickness oxide is increasing, your Vth will increase. So this is one thing, you can note it down. So what is, if we see graphically, if we are increasing this oxide thickness, so what is the equation of Cux? Cux equal to epsilon to x upon Tux. So if we increase our Tux, your Cux will increase. If we increase our Tux, your Cux will decrease. And if oxide capacitance is decreasing, our current will decrease. Why the current will decrease? If we see the formula of current, it will be like this. So Id will be equal to 1 upon 2 mu n Cux W by L. So if this term, if this Cux will decrease, correct, your current is going to decrease. So in turn, if we see, if your oxide thickness is increasing, your Vth will decrease, and in turn your current will, if your thickness oxide increasing, Vth will increase, in turn your current will decrease. So again we'll see this formula. So VTH is equal to VT0 gamma. So we can see the direct relation between VSB and phi. If source to body voltage is increasing, your VTH will increase, correct? What is the other thing? If we see gamma, in this gamma we have this term Na. Na is a doping. So what we can see, if your doping is increasing, VTH is also increasing, correct? Because this is a direct relation. So if Na or doping is increasing, your gamma will increase. If your gamma will increase, directly your VTH will increase. So if we see the combined effect is, if your VSB is increasing, your VTH will increase. If your thickness oxide is increasing, your VTH will increase. If your doping is increasing, your VTH will increase. So in the end we will see what are the types of VTs we are having. So let's say we are defining a reference VT. So that VT is called a medium VT, correct? And by changing other parameters, we have achieved a VT which is higher than your reference VT. So that VT will called as a high VT, and by changing the parameter, we have achieved a VT which is less than your the reference or medium VT, that will be called as low VT. So where we can use this high VT, where we can use this low VT. So if we see in the low VT, obviously if your VT is low, your current will be high, correct? So if VT is low, your delay will be less. If your current is high, delay will be less. So in the LVT, delay will be less. In the medium VT, delay will be medium. High VT, delay will be highest. Why? Because delay is inversely proportional to your current. What does it mean? In LVT, current is highest, that is delay is less. In the HVT, current is lowest and the delay will be high. But the one implication is, we cannot always use LVT cells. In the LVT cells, leakage used to be the highest. So that is a limiting parameter in the design. So that thing we'll see when we'll see our power intent in the design. So as of now, so let's say we are having a design, or we are having a cells which is giving a high high delay. So what we can do, we can change that cell, or we can use same cell with different VT flavor. So this we can replace that HVT cells to LVT cells. So these are called flavors of the VT or the VTH flavor. So as of now, this is more than sufficient, and then we will cover the other things. So in the end, please like and subscribe my YouTube channel. Thank you.